Okay. So let's get started where we left off on Wednesday. So we've been talking about matched asymptotic expansions. And the idea here is that often a perturbed ODE or PDE will have an order 1 solution, which we'll also call the outer solution, which does not satisfy boundary conditions, initial conditions, or match across an interior layer of the problem, right? So, for example, we may have our outer solution here, right? But our boundary condition could be here, okay? This is going to create what's called a boundary layer. Okay. We can also have situations that we'll talk about where maybe across some region of the interior of your problem, you can define two different outer solutions, right? But then in between, you need some rapidly changing but still smooth function that can connect these two outer solutions together, okay? This would be called an interior layer, okay? And another thing that might happen is that you may have an interior subregion where you have two outer solutions that come together, but they don't do so discontinuously. And so for this, you need something called a corner layer, which will allow you to smooth out that discontinuous derivative of the outer solution, okay? So over the next few lectures, we're going to build up the ideas behind doing this. The general idea of matched asymptotic expansions essentially is to take some inner variable, we'll call it x bar, okay? And this will have form x minus x0 over epsilon to the alpha. And we don't know what the scaling of this inner variable is, okay? But this is the argument, this is the independent variable of our solution to the ODE. X0 is going to be kind of the anchor point for your boundary layers or interior layers. So it would be like, you know, x0 equals 0 here, right? If this is 0 and this is 1, it could be like x0 equals a half here, okay? And by plugging this in to your perturbed equation, you can specify this by the distinguished limit. Essentially, you have to choose your alpha so that the terms that you involve in your expansion, at least one of them is like, you know, a higher order derivative that would not be included in your outer solution typically. This often happens if you perturb the highest order derivative in your ODE. Okay. So this is essentially what we're going to do for the matched asymptotic expansion method. Okay. And so the steps we outlined at the end of class on Wednesday, okay, were basically to determine this scaling epsilon to the alpha, okay, and the location of boundary, interior, corner layers, okay, and that's going to be given by x0. Find our outer solution, and then our inner solution. And the last step really is to fix constants using boundary conditions, okay, and matching inner to outer, okay. We'll talk about how to do that today. And then the last step would be to create what's called a composite solution, where you subtract off any redundant parts in your inner or outer solution. So we'll unpack that a little bit today. Okay. So as we often do, I'm gonna return to our problem from before and sort of look at this by example. Okay. So remember the problem that we talked about originally. Okay. We had y prime prime, sorry, plus y is equal to epsilon y for sorry, went back too far on our example. Okay, so sorry, our example is epsilon y prime prime plus y prime plus y equals 0. Y0 is equal to A, y1 is equal to B. And this is our problem that we'll call d epsilon. And then remember our d0 problem was just y prime plus y equals 0, y0 equals A, y1 equals B. Okay. And that's what gives us our outer solution. Okay. And what we worked out was that when epsilon equals 0, right, we have the d0 problem, and we have that y is equal to a e to the minus x. I'm going to put a subscript of 0 there, and let's call this our outer solution. Okay. So that's one of our first building blocks of our solution. Okay. And so the question is, right, if we have this outer solution, remember what it's going to look like. We have y here and x here, and we have some exponentially decaying function, right? We don't know where these boundary conditions are, but just for illustration, let's put them at two different parts right here. Maybe drop it down here or something like that, right? So you can imagine we could slide this around and satisfy one of these boundary conditions by changing A, but we can't satisfy both, okay, because it's rigid, okay, and it's just going to move up and down as we scale it. Okay, so unless we get lucky, we're not going to satisfy both these boundary conditions. Okay, so then let's focus on maybe the left boundary and trying to build some inner solutions such that we can stitch it together with our outer solution in order to satisfy the boundary condition. Okay, so the idea here is that we want to identify some scaling near x equals 0. Okay, and in particular, we're going to let, and for now, I'm going to call this variable xl is equal to x over epsilon to the alpha, okay? And then we'll write y of x is equal to y sub L x sub L, okay? Now, if we differentiate this with respect to x, we can use the chain rule to write it as dyl dxl dxl dx, right, which is going to give us epsilon to the minus 1/2 dyl dxl dy d2yl d2y dx squared is going to equal epsilon to the minus 2 alpha d2yl dxl squared, okay? So then epsilon to the 1 minus 2 alpha d2yl dxl squared plus epsilon to the minus alpha dyl over dxl plus yl is equal to 0, okay? So in order to make d2yl dxl squared significant, right? This is our distinguishing limit. We need to match 1 minus 2 alpha to the min of minus alpha and 0, okay? So because we're going to take alpha positive, right, in order to squish this variable so that it just lives on a thin boundary, right? So the idea here is like, if you move this epsilon over to this side, right, you have that x equals epsilon to the alpha. So in order to make this coordinate that's smashed against 0, we need to take alpha to be positive here, okay? So that means that minus alpha is going to be the minimum of this. So our equation is just 1 minus 2 alpha equals minus alpha is going to give us the distinguishing limit. So our distinguishing limit here is then going to be just alpha equals 1, okay? And that means the boundary layer has width epsilon, right? Because once XL gets above order 1, right, and starts getting into 1 over epsilon, right, this is no longer sort of an inner layer solution. You're bleeding into the outer layer at this point. Okay. All right. So just a quick note, right? If we choosing alpha equals 1/2 would make the middle term leading order, right? So if we try to match this and this, right, this term would end up winning out, okay? So that's not a good distinguishing limit because we're not involving the higher order derivative, which is excluded from the outer solution, okay? All right. Now, by the same token, if we wanted to look at the right-hand boundary, okay, it also has width epsilon, essentially by the same logic, okay? So you could go through a similar analysis where you take XR, for instance, is equal to X minus 1 over epsilon to the alpha, right? If you plug that in, you'll find that yeah, that no, I think I need to switch this down here. Yeah, if you plug that in, you'll again find that alpha has to be 1 in that case. All right. So now let's talk about our expansion. So in the middle, right, we're going to have that y is equal to, and just for now, I'll subscript all this y middle solution, which is going to be y middle solution 0 plus epsilon y middle solution 1, and so on, right? That's our sort of outer solution. On the left-hand side, we have XL over epsilon. Y is equal to YL of XL, YL 0, X plus epsilon, YL 1, X, and so on. And then on our right-hand side, okay, so I guess I am going to switch this back again. I'm writing too fast here. This would be XL over epsilon. And then I will make this, I'm going to change this back to what I had it before. I'm indecisive about this. It doesn't really make a difference, but it's whether you generate some additional minus sign or not. Okay. All right. All right. So your right-hand side, right layer, you're also going to have this epsilon width boundary layer. Your left-hand side, you're going to have this epsilon width boundary layer. Okay. And so that means that just over an interval of that size, whatever epsilon is, you're going to get some rapid change in your solution that's going to connect you from your outer solution to the boundary. Okay. And note that in this case, on the right-hand side, this is going to be less than or equal to 0. And y is going to be equal to yr xr yr 0 of x plus epsilon yr1 of x and so on. Okay. So finally, let's start figuring out what these inner solutions are. On the left boundary, after matching, we're going to have d2yl dxl squared plus dyl dxl plus epsilon yl is equal to 0. Okay. So at order 1, we end up with d2 yl0 dxl squared plus dyl0 dxl is equal to 0. Okay. We can solve this. It's not hard. Just YL0 equals some constant we'll call AL0, BL0, e to the minus XL. Okay. Now, if we wanted to go up to order epsilon, we would get d2YL1 dxl squared plus dyl1 dxl plus YL0 is equal to 0. And we could solve this, right, just using undetermined coefficients or something like that. Okay. For now, we're going to focus on this order 1 solution in the boundary layer. And in particular, we want to satisfy y0 equals a. Okay. And so that means that we take this, right, and we just apply that boundary condition. Okay. So if we do that, we get AL0 plus BL0 is equal to A. Now we have two constants. So the way that we'll specify another equation for a constant is by what's called a matching condition. You need the inner solution to come together with the outer solution. And we can do that essentially by taking a limit as XL goes to infinity. As you leave the boundary layer, you should then connect with whatever the value of your outer solution is. Okay. So in the middle now, in our outer variable, we're going to have epsilon d2ym, the middle solution, dx squared, but it's in standard sort of x coordinates, dym dx plus ym equals 0. And there, remember, we had at order 1, we have this first order differential equation that we already solved for. And then at order epsilon, we have d2y m0 dx squared plus dym1 dx plus ym1 is equal to 0. Okay. So remember, way at the beginning, right? We got this outer solution. Okay, we can get that again. Now we're gonna grab all our solutions first before we write down the matching conditions, and then we'll sort of represent what happens at the interface between them. Okay, our right-hand solution now is going to have a differential equation like that. Okay, but at first we're just interested in 0th order, and typically that's what you do for these problems. dxr equals 0. Okay, so we end up with yr0 equals ar0 plus br0 e to the minus xr. Okay, now we would have something similar to what we had to the left-hand case. Okay, but let's look at the boundary condition now. If we take y of 1 is equal to b, that's going to imply that just for the 0th order equation, the first order equation, ar0 plus br0 equals b. Okay. Coming from there. All right. So far we only have that boundary condition, and then we need these 3 other equations. So we have 5 free constants and 2 equations. Okay. Matching is going to give 3 other equations. All right. So if we look at our situation now, you can sort of draw a picture of what you think is going to happen. And this can be a good guide, right? So I have some boundary condition here, right? I can maybe just slide the middle solution here down so that it matches y of 1 equals b. And we'll show that's what happens. And then this is our left solution here, yl0. And it's going to connect together with the middle solution here, while also satisfying our left-hand boundary condition. Okay, so this is what the matching process is going to do for us. Is it's going to allow us to specify our constants as we need there. Okay, so the idea with matching is that we have some overlap region, okay, where both equations hold, right? So basically the inner and outer equations hold, okay? YL of XL should be approximately equal to ym of x, okay, as x goes to 0, or as XL goes to infinity, okay? So XL infinity is sort of coming from the left, and x equals 0 is coming from the right. XL goes to infinity, right? So you have to imagine that within the inner region, you're in the squashed parameter region. In order to get out of it, you need to send that inner variable very large in order to break into the order 1 size variables that would be to the right, okay? So one way to sort of handle this, right, although, you know, it turns out in the long run, we don't always necessarily have to do this, but this is a way of sort of kind of carefully mediating these two regions, that we have an intermediate scaling where we might take x equals epsilon to the beta times x hat, and this is going to go to 0, okay, and XL is equal to epsilon beta minus 1 x hat is going to go to infinity as epsilon goes to 0, okay? So if we choose beta equals to a half, okay, we're going to be living in this intermediate scaling that sort of bridges the inner and outer layer, okay? So in that case, YL 0 equals AL 0 plus BL 0 e to the minus epsilon beta minus 1 x hat, okay? And this is going to be exponentially small as epsilon goes to 0, say, plus some order epsilon terms. Ym0 is going to equal AM0 e to the minus epsilon to the beta x hat plus order epsilon terms, right? This is going to be approximately equal to AM0 minus epsilon to the beta x hat AM0 plus order epsilon terms, right? As epsilon goes to 0, okay? So this implies that AL0 is equal to AM0, right? Now you could just take those limits if you want, if you don't want to sort of deal with the intermediate scaling, and you get the same equation in that case, okay? So this is what matches your outer and inner limits, okay? So kind of the quick way would just essentially be to take XL to infinity in YL 0, okay? So that would send you to just AL 0, and then X goes to 0 in YM 0, and that would send you to AM 0. And that would equate those two, right? So in general, it's fine if you just do that. You don't always have to do intermediate scaling, okay? So that gives us another equation, right? This is our third equation now, okay? At the right end, okay, we can take the intermediate variable, okay? X bar is equal to x minus 1 over epsilon to the beta, less than or equal to 0. YR 0 is equal to AR 0 plus BR 0, e to the minus epsilon to the beta minus 1, to the minus, epsilon beta minus 1, x hat plus order epsilon. Ym0 is equal to AM0, e to the minus 1 minus epsilon to the beta x hat plus order epsilon. So this is approximately AM0 e to the minus 1.
Does x have to be x bar?
Oh yeah, you're right. Yeah, sorry, I wanted to use x hat there.
Okay.
So I want to put a hat on it. I just want to make it different than our other change of coordinates that we used before. So. Okay, so epsilon to the beta in that case, x hat AM0 e to the minus 1 plus order epsilon terms there, okay? So this is going to imply then, okay, that we want BR0 should equal 0 in order to prevent exponential growth, okay? And we want that A R0 is equal to AM0 e to the minus 1, okay? So on the whole, what we end up with is AL0 is equal to E times B. BL0 is equal to A minus E times B. AM0 is equal to EB. AR0 is equal to B. And BR0 is equal to 0. Okay. And that means that YL0 is equal to EB plus A minus EB, e to the minus XL. Ym0 is equal to EB, e to the minus X. And YR0 is equal to just B. Okay. So you see here, right, you don't really need this right-hand limit because this is tending to the correct limit as x goes to 1. So it's fine in this case. But we've prevented this, right, from blowing up as x goes to infinity. Sorry, as x hat goes to minus infinity, right? So that's going to exclude this exponential term here in this case. All right. So let me just sketch out then what's happened there, and let me just kind of label everything. You formulate all these equations, and then you just solve them. You usually get, maybe some messy algebra involved. But the situation now, if we draw it, is that we have x here. I'm going to draw the line x equals 1 here. This is the line x equals 0 here. Here's y of 0 equals a. Okay. Here's the value EB here. And then let's say down here is B. So what happens is in your left inner layer, you get this rapid drop here. Okay. And that's going to be your boundary layer. Okay. And then in your outer layer, you have much more gradual drop, okay? And you hit this right layer here, right? Where you don't really need a boundary layer. So a boundary layer is not needed here on the right because you can tune basically that outer layer solution to match as needed. Okay, so that's the general idea. You have a couple problems on your homework where you are going to practice this. I think problems 4 and 5. Okay.
Could we have done it a different way where we ended up with a boundary layer on the right and not the left, or is there a reason that it has to vanish on the right?
Yeah, so again, the problem with doing the boundary layer on the right, and you would see, is that you have this exponential function here, and that's your rapidly changing function. So because that function is necessarily going to blow up as you move away from the boundary, there's not a good way to make that stitch together. You need exponential decay in order for that to work. So that's why you can't use the.
So are we kind of assuming that B is less than A then? Like, couldn't you have everything flip up, like right, left, and top, bottom?
Um, I think either way you're gonna have this exponential here that's going to blow up. So yeah, I mean I could draw another version of the problem, right? Where we maybe we have A here and B up here or something like this. And you could also have exponential decay up to a value here, right? And then you have the outer layer sort of decays this way, for instance.
Okay.
So I think you still don't get around the issue that the right-hand layer, right, is going to be problematic because you have that exponential blow up in that term there. So no matter what, you're going to select the left-hand side as the boundary layer. Okay. Because these equations that we wrote down, right, they didn't assume anything about the
Right.
relative values of A and B.
Yeah, like it makes sense from the equations, but I guess I'll just have to do some convincing of myself.
Yeah, I mean, the example that I drew was this, right? But the equations that we worked out, they could also apply to this case as well.
Right.
You just get different signs. So you could try, yeah, you could try it with different values of A and B and see that you get the boundary layer. So yeah, when you're doing these problems, you can approach it 2 ways, right? Like you could keep things general, right? In which case, yeah, it just gets a little bit more clumsy with all the subscripts and stuff. Or you can sort of sketch at intermediate points in your problem and try and rule out, different possible solutions. You could try a boundary layer just on one side at first and see if that works, and then a boundary layer on the other side. But the intuition of this problem is that you can certainly satisfy one of the boundary conditions. So you should only need a boundary layer on one side. It's just a question of which side it should be. Okay. So I want to talk now about how to build the composite expansion. All right. And the idea is that you just add the inner and outer solutions, but you don't want to double count terms. Okay. So you write the inner in terms of the outer variables. So then YL0 would equal EB plus A minus EB e to the minus x over epsilon. This is going to be of the form EB plus order epsilon terms. And then there's our outer solution. Just preface it. So then we'll write the outer in terms of the inner variables. Okay. Ym0 is equal to EB e to the minus epsilon XL. So this is approximately just EB plus order epsilon. Okay. So now this tells me that if I'm adding them together, this term EB is going to show up twice in both of my equations, right? I get it as a coefficient of my exponential term as I come out of the inner layer, and the value of the inner solution that I would be adding to it. By that same token, if I'm moving around in the inner layer, I have this EB term here as a constant, okay? But I'm also going to have it as I shrink down into the inner layer here, my outer solution. So that means that what we have to do is we have to subtract the double count of that constant EB. So that means that my composite solution is going to be EB plus A minus EB e to the minus XL. Okay, so this is my inner solution, YL0, plus EB e to the minus X. This is going to be my outer solution, YM0. And then I'm going to subtract off the double count EB. Okay. So then at the end of the day, I get Y is going to be given by A, or asymptotically given by A minus EB, e to the minus X over epsilon, plus EB, e to the minus X. Okay. And my error is going to be order epsilon over all X, right? Another way to think about this is as we sketch this out, right, I've sort of drawn it like I'm sort of drawing a piecewise smooth function here. But in order to have something useful, I really need to take my outer layer solution and add it to my inner layer solution. So whatever value they're coming together at here, when I add them together, that's going to get double counted. So this is the value that needs to get subtracted off when you perform the composite solution approximation. Okay. Now, let me see what I want to do. I got about 5 minutes left. Let me just, pause and see if there's any questions so far. All right. Okay, so that's our steps, right? We start off with for a boundary layer problem, right? We can start off by just getting the outer layer solution, find the inner layer scaling, okay? Solve inner layer problems, okay? Match to PCs, okay? Then we go to match inner and outer, okay? and then we form the composite solution. Okay. And essentially everything that we'll do in this section of the course is some variation on that. Okay. So you can go to higher order terms. It gets a bit more messy. So I'll just say if you want higher order terms, right? In this case, we can go to order epsilon in each region, right? Remember those order epsilon equations that we wrote down before, okay? Now we can solve this, right, for YL1, YM1, and YR1, okay? Matching will follow the same procedure, okay? There's not really a lot new in that case, right? You perform the matching, right? You compute your composite solution, okay? And so you can see Holmes 2.2, I think. Or no. Yeah, I guess this is a different example, so I don't know. All right. I can't just give that to you to read. Let's. I only have like 3 minutes left, so let's go through that next time rather than me starting on it now. Okay. So what's to come next week is we're gonna look at a few more examples of matching. Okay. For boundary layers. Okay. I'll briefly go through that example of getting higher order terms. Okay. I'll talk about interior layers. Okay. Where you have to find x0, where that's going to be the location of your interior layer. I'll talk about corner layers and how to get them. And that's where you match discontinuous derivatives in that case, right? But the basic procedure is always the same. You have a scaling variable. Maybe you have some scaling of your actual function in a couple of these cases, okay? But in general, you're just gonna solve for your outer solution first, perform some reasoning with respect to where you should expect these layers to be, okay? You can sometimes rule out where they'll be based on the restrictions of the actual differential equation, and then you can identify your scaling and solve the differential equation to get these inner layers. All right. So if there's no other questions, I guess we're done for today. And I'll see you all on Monday.
Thanks, Zach.